Welcome. I'm here to give you an introduction to data science and machine learning, kind of demystify those terms that get thrown around a lot in industry and in media a lot. Everything from, let's see, I think way back when with Terminator, AI was thrown around, and now with ChatGPT, it's really popular and the hot topic in media. Every startup in the world throws AI in what they do just because they can at this point. So getting to some of those terms, what they actually mean, how to actually find tools to do what you want with machine learning and artificial intelligence. And yeah, hoping to get to demystifying some of that stuff for you. Awesome. Alrighty, so as I've kind of said, it's a term that gets thrown around a lot. It feels like with a lot of these applications, a magic wand that is waved at a problem, and all of a sudden it's solved. In reality, it is a very specific tool or set of tools that needs very specific parameters to actually get at the underlying functionality and use some of that power of an incredibly powerful technology, but it's not really magic. I think a lot of people have experienced that most recently. If you've played around with ChatGPT, it does make a lot of fun little mistakes that come up. So we're really looking at what we can actually use machine learning and artificial intelligence for and what that actually means. So what you really need for artificial intelligence to work or machine learning is a scientific or mission goal. You need a specific task that you are trying to solve. Because this falls under data science, you also need data to learn from in the future. When looking at the models and the machine learning solutions that you're looking at, you also need metrics to understand how it's actually working and knowing that you're actually getting closer to success. So without good evaluations, there's no clear way to define success. And all of these models need a way to understand what success actually means to them. So those are kind of the three main things that are important for actually defining your task and looking at what you're trying to do. And then the most important for doing it right is definitely the partnership. So you need to look at data scientists and domain experts, subject matter experts, to actually build this system that functions in an effective way that people are actually going to be using it. There are a lot of models that have been built out there, a lot of machine learning and artificial intelligence solutions that no one's ever going to use because the person found a data set, built a model, and it's not useful for anything. But they wanted to, and it exists now. So that partnership, actually understanding your problem, understanding what the domain scientist needs, and understanding what the tasks that you're actually doing is incredibly important. Alrighty, so what is artificial intelligence? Is a very, very broad term that is creating machines that can do things that are traditionally only done by humans or that require human intelligence historically. Machine learning is a subcomponent of artificial intelligence. This is, we'll get into the specific definitions of that. And then you have other terms like deep learning and data science, which deep learning is a very specific type of model. We'll talk a little bit about that today. And data science describes this broader science that actually, some of it exists outside of artificial intelligence. Alrighty. Hopefully this hierarchy makes sense. Okay, so what is artificial intelligence? Again, it's a very broad term. So this it normally requires human intelligence. They're doing a task that normally requires human intelligence, such as speech recognition, decision making, or translation. You can think about a lot of the tools that we use today, like Google Translate, that are out there that are integrated. You have autocomplete probably on your phone now. And those are all kind of falling under the artificial intelligence domain. So there's this kind of defining AI where you have this optimal behavior. So acting humanly and acting rationally are on the bottom here. And then thinking rationally and thinking humanly is a completely different thing. So from a functionality perspective, machine learning and artificial intelligence might look like they're effectively solving a problem, but they're not thinking about it the same way that you or I would. They're not thinking at all. All right, so there are two historical classes of artificial intelligence. There's symbolic, which is this handcrafted rules-based logic that is often actually forgotten in AI. But unless you're talking about what your company does and you want a better stock price, then you're definitely doing AI. These rule-based systems and formal logic are very much based around what we've considered traditional programming. So think about spell check. Spelling and looking for grammatical mistakes in language or in your Word doc, that's been around for a very long time. And a lot of that was rules-based. So someone actually programmed the grammar rules and the proper way that words were spelled into Microsoft Word. And that is kind of the symbolic or rules-based artificial intelligence. It used to be something that required human intelligence, and now we've kind of solved that with that problem. Then there's the much more popular category now of artificial intelligence, the statistical learning. So the statistical takes in machine learning, probabilities, and inductive inference. So this is what we're going to talk about today. This is what all of the tools that you've seen kind of categorized as artificial intelligence in the recent time frame are actually doing. And this is where you can actually leverage the data that exists in our very online world now. So it is largely driven by observational data, and it is all about getting certain statistics and utilizing statistics of that data. Alrighty. So machine learning algorithms are built to find these statistical patterns in your data. Some of the types of algorithms that you may have seen around are linear logistic regression. This is the very most basic type of algorithm. There are tree-based methods, which we'll talk about a little bit today. Support vector machines, which are incredibly powerful. And then you have your traditional Bayesian models and your neural networks. So neural networks are in that deep learning category, and they really cover a lot of what the amazing applications that I'll talk about today actually are utilizing. Okay, so what can we do with machine learning? So machine learning has been used to solve a lot of problems and a lot of business use cases in the world, but what is it actually doing? So some of the subcategories of things that you can do with machine learning are like classification. So determining what the actual label for something might be. And we'll talk a little bit more about that. Forecasting, what are things going to be in the future? I know that everyone in my grad program tried to forecast stock prices and get rich quick when they learned about machine learning. It didn't work for any of them, but we all tried anyways. There is clustering, which allows you to utilize data that might not have labels, which we'll talk about in a little bit more detail. You've probably played around with Google Translate, with machine translation, or other tools like Babel, which can now do real-time audio to audio translation, which is an incredible technology driven primarily by deep learning with natural language processing. There is also generative art, if you've played with Dolly, which is really fun. And you can ask it to make anything. And there's some interesting data issues with some of those models, but we can talk about those a little bit later on. Then there's the category of reinforcement learning, which I'll talk about that in a second. That one's very fun and allows a whole powerful new category. All right, so let's get back to we've talked about observed patterns or statistical patterns, and that's kind of what I've talked about with machine learning so far. But let's really put let's really get down to the definition of it. Let's talk about it in very key components, what you need for something to be machine learning. So machine learning is a computer program that is said to learn from experience E, some class of tasks P, and has a performance measure P. So the idea is you have your task P measured by P that improves with experience E. So if that doesn't make sense right now, don't worry. We're going to stick with this definition for a bit. So one of the really common problems that machine learning has been used to solve historically is handwriting recognition. So actually, this data set, the MNIST data set, exists out there. It is one of the most common computer vision data sets that everybody starts with when they're getting started with computer vision or machine learning. It's solved as a problem, and it is used today by the post office to actually read and interpret zip codes on packages, and removes a lot of the tedious work that was done sorting letters at post offices. So practical applications of machine learning. So the task T in this case is to recognize and classify handwritten numbers within images. The performance measure is the percentage of numbers correctly classified. And the experience that we're looking at is this database of handwritten numbers with classification. So that's an important distinction there. A database of handwritten numbers is just fine, but the key thing that it has is those labels that actually tell you what's in the image. So in this case, we have, it's a little small, but this 0 has the label 0. And that might seem trivial, but it actually tells our model what to learn. I realized I was sitting in the lobby, not in the day 5. So I'm looking at questions now as they come in, if you have any. So looking at this problem, the artificial intelligence here really sped up the process of delivering your mail. And this is kind of one of those really simple examples of classification. Let's look at something a little bit more interesting. So talking about machine learning in a little bit of a different setting. So we have our data and experience. This can look a lot of different ways. So you can have data that is images with those labels, like in MNIST. You have data that can be like a CSV file that has information about housing prices or stock prices or whatever you're looking at. You can look at COVID prevalence in an area to try and predict how the disease is going to spread. And this data can very much vary in what you want to use. But the important thing is you get it into a format that your model can actually use. That's the second component, your model. This is actually the function that takes in your input and gives you some output and what that actually looks like. So you have your data, your experience, your model, the thing that actually changes stuff. Then you have what is called a loss function. The loss function here is what actually tells you, it's your performance metric. It's what tells your model that it's getting better or worse. The loss function has to be machine interpretable. It might not be super meaningful to you or your mission on how it's working, but the closer your loss function is to actual performance you want to see of your application, the better your model is going to be. So I see there's a question about ML and comparing handwriting. It's a very cool task. The field of forensic linguistics is blooming right now. So there's actually a comparison of handwritings being done by a lot of folks that are looking for criminals. So there is a field of linguistics that does handwriting analysis, and now machine learning is helping with that to determine what someone's intention was when they were writing something or who wrote something and those kinds of things. And it's actually being used to solve crime right now. So looking at this is an example of a decision tree. It's one of the most intro basic machine learning models that a lot of people use. It is fantastic for what this is called, this tabular data, your CSV files or whatnot, where you have all these categories of data. So this is solving the critical problem for the world of will Bill play tennis today or not, given the weather observations. So our target here is playing tennis, and this is what we're trying to predict, play tennis or not, and our input is the outlook, the temperature, the humidity, and the wind. So machine learning algorithms take a set or sequence of vectors as input. The raw data must be formatted into this component. For many types of data, there are existing encoding conventions. Natural language processing is a very common example of this. So the existing encoding conventions there are built from these very large models that already exist by folks. There are also methods of encoding very much various types of data. And what's really important there is you just got to know how to get it into the format that the computer can actually process. There's a lot of human interpretable data that isn't ready for prime time the computer at this point. So one of the things that comes out with that is this feature engineering. So how do we get the domain knowledge from someone that actually knows what you're trying to do into these encodings? And how do we not tell the computer something that we actually don't want it to know? One of the common ways that this problem came up in the past was people would label their classes 1, 2, and 3. And what that did was it actually implied a relationship between the classes. So 1 and 2 were closer together, and class 2 and 3 were closer together, and 3 was above 1. And that relationship does not exist regularly when you're trying to classify whether something is a dog or a cat. There's no linear relationship between that. So looking at these vectors and how we're actually encoding this, there's a lot of choices that you can make here. So you can do sunny, overcast, rain as our weather. You can do sunny, partially cloudy, mostly cloudy, cloudy, drizzle, rain, downpour, hurricane, all the way out as far as you want to be descriptive, or you can just give it an image. And you have to decide what the best choice for your application actually is, given what time you might need for that and what you're actually trying to do and what information actually you need to convey to solve your problem. So decision trees learn based on this information theory called entropy. I don't need to get into the nitty-gritty details on there, but that's kind of the learning algorithm that is being done here. So I see a question in the chat that is a fantastic one, so I'm gonna pause for a moment. Do we have machine learning applications that can feature engineer for us? The answer is definitely yes, and deep learning does a lot of that for you. When you have more and more data, you can actually let the model do some of the feature engineering for you. And there are some caveats there, like making sure the model is actually learning good features and not just some function of your data. I think a common one does like CCT footage, and like it had a label in the corner and it just was fed into an image processor, and it would only ever look at the label because it was blasted over the image. So it learned features, but the features were cheating. So that's something to look for when you're doing automated feature engineering, because you can't add that human intelligence. Okay, so trying to play tennis, looking at how this is split. So looking at outlook, we split based on the 3 categories here: sunny, overcast, and rain. Comparing what happens when it's sunny, looking at those conditions, what happens when it's overcast, looking at those conditions. And now we've kind of made this branching logic. This actually looks like a lot of traditional rules-based methods, and that's why decision trees came about, but it is learning these rules from the statistics of the data. What's actually present in your data. It's not reasoning, it's just using this performance metric and using the splitting method. Okay, so looking at this decision tree, what we do is we go down through the branches here, looking at whether or not it's sunny, and whether or not the humidity or wind are high. So this kind of gives us a way to look at and determine if there's going to be tennis played today. So what will happen on a sunny, cool, humid, windy day? Give you a second to throw your answers in chat if you're interested. Alrighty, didn't see any pop-ups, so who knows? So looking at this, it's sunny, looking down this, it's cool. That temperature wasn't actually necessary for our tree's decisions here. So regardless of temperature, we can predict what's actually happening. So decision trees are very easy to interpret. It's easy to tell what they're doing and actually look into the model for that. And that is a big, powerful thing when it comes to a lot of machine learning methods. When we talk about deep learning methods, we actually don't get that interpretability. So we can tell that temperature really doesn't matter for this person's decision to play tennis or not. And humidity only matters if it's sunny, and wind only matters if it's rainy. So this is an interesting interesting thing that comes out when your data that is very much reflective of your data. There is also very much a bias in this data here, in that I don't think we're looking at all of the indicators of whether or not this person is going to play tennis. I don't think that we can learn from this data specifically and get 100% accuracy on, yes, they're definitely going to play tennis. I think there are some extraneous factors outside of this, like if they break their leg, they're probably not going to play tennis for a while, and that's not captured in our data. So understanding what's captured in your data and what you're actually trying to do with your targets and whether it answers that question is an important thing to consider when you're looking at how you want to use these systems. Alrighty, so machine learning models, as I've said, are often just components of larger systems, and you must have a clearly defined task that you're trying to solve. So what is your task be? For the model to be effective, it has to answer the correct question. How does it fit into your larger system? What task is it actually trying to accomplish? What domain knowledge do we need to make sure we get into the model, and what data is available? Like going back to our letter sorting example, it's not just the broader system is getting letters to the right place, but you're not asking the model like, hey, where does this letter have to go? You're asking it what numbers are on this letter, what zip code is on this letter, and that is the subtask that you're trying to get at with your model. It's important to get down to the very specific question there, because then you can create a model that is tailored directly to that. The more abstract you get, the more issues you can run into if your data doesn't represent that. One of those questions you can look at if you're looking at something like toxicology. So looking at whether or not something is toxic, you can ask that of your model, like, is this thing toxic or not? Label all your data, such as the chemical compound is toxic. But what you're actually asking there is a lot of different questions. So is it respiratory toxicity? Is it liver toxicity? Like what subcomponents actually exist under there are really important. So you would much rather ask the subtask so the model can learn a little bit better. I hope that makes sense. I haven't seen any questions in the chat about it. So this gets back to that partnership. ML experts know your models, subject matter experts know your domain, and the mission subject matter experts know what the real world goal is. Like kind of this boots on the ground perspective of what you're trying to do. All right, so let's talk about types of machine learning problems. So types of machine learning that comes up very often, there's three really common categories. We have supervised learning, unsupervised learning, and reinforcement learning. These are very broad and used for a lot of different things out there. The most common that you'll probably see a lot of the time is supervised learning. Unsupervised learning is a lot of that feature engineering where you don't have labels. So let's get into it. What are we actually looking at here? So supervised learning is all of the examples that we talked about so far have been examples of supervised learning. So pretty much it's when your model gets the copy of the answer key. So we have some inputs or features, X, we give it to the model, we get some output from the model, and then we just compare it to what the desired output was. Supervised learning requires labeled data points. So the amount of labeled data you have, like I mentioned, those images, used to classify the numbers on the letters have those labels that actually tell you what number is in the image that the model can actually learn. Getting good data is the important part of being able to do supervised learning. So supervised models train on representative data. It's important that your inputs that you give it when you're training look like what you're going to try and see in production. Like, one of the things that comes up is if you're doing an experiment in a laboratory setting and you train your supervised method on only examples that you see in the lab, if you put that on a fieldable sensor that actually is sitting out in the middle of the desert somewhere, it's likely that the background is going to be very different and the inputs are not going to look like your outputs. So you want to make sure that you have a model that is capable of handling that situation. There's no guarantee that it's going to be able to generalize to new types of data or new parts of the input space, as we refer to it. So making sure you create either a robust model or you know exactly what it's going to be used for is very important. So this is an example of supervised learning. This is a binary classification. Is this pneumonia caused by COVID-19 or other causes? Looking at chest x-rays, it was 98% accurate. So the input images are fed into what is called a convolutional neural network. And the output is COVID-19 or not COVID-19. Given this example and what I've talked about with input data, you wouldn't throw this at MRIs or anything like that. The images that it's expecting are these formatted x-rays in this format here. And making sure that you are looking at these types of x-rays and in the specific location is very important when you're talking about your task here. Another really interesting application in supervised learning is AlphaFold. So AlphaFold was this incredibly powerful tool that utilizes a lot of the most modern deep learning architectures that we have and predicts a three-dimensional protein structure. So you give it a sequence, it gives you the coordinates of the folded protein based on this model that is called a transformer, which is a very powerful deep learning model that powers a lot of the things that we see today, and solves this problem that is incredibly challenging. Like, predicting the structure of a folded protein is something we've been trying to do for a very long time and takes experts incredible amounts of time to actually understand how these proteins are going to look. So unsupervised learning, I see there's a question related to it in the chat, so we'll talk about this first and I'll get to it. So unsupervised learning, what if we don't have any labels? What can we do with our data? So instead of getting to like this target output, instead we replace the outputs with another goal. Autoencoders try to compress the data down and then recreate it. Clustering algorithms try to create key clusters within your data and kind of look at sub clusters within there. There are also methods of semi and self-supervised learning, which use the data that you have to kind of create labels and kind of make a supervised learning task with these meta labels. This is a very powerful tool for utilizing in a lot of spaces where you might have a very limited amount of labeled data. One of the other things that you may have heard of is generative adversarial networks, which are these generative models that can actually create new things. And DALL-E is an example of a generative adversarial network that actually creates something, creates an image. And the performance metric that you have there is not some classification. It's not something that you're looking at there. So someone asked, how do you consider using supervised and unsupervised ML for microbial networks, especially in real applications in sustainable agriculture? So looking at that in a very broad context, if you have a labeled data set when you're looking at the data, you can look into supervised learning methods for trying to build applications of sustainable agriculture. But when that data doesn't exist, what you can do is use unsupervised learning methods as a data analysis tool. So looking at these clustering algorithms and trying to see patterns within the data using these unsupervised methods. And then you can also use semi-self-supervised learning to bolster the amount of target data that you have, and use some of those methods to create more data and do kind of this human-assisted development, or human in the loop models. So when you're going into a domain where they might not have a lot of labeled data, sometimes the task that you're looking at is creating these labels for future development in this area. You can also use machine learning in areas that are very well studied, where you have a lot of data, and create a model that can generalize more to areas that are not as well studied. I don't believe we get into that in this presentation, but that method is called transfer learning. And you can look up that key term, and it is a very powerful tool that is commonly used in machine learning. Yes, one of the things that comes up is some people don't know they're using machine learning, but it's just simple regressions counts as machine learning. That's fantastic. So autoencoders, this is one of the methods I talked about. The goal that comes out of here is to just recover the image. So here we have an image of a shoe, and on the output, we have an image that kind of looks like a shoe. And that's what we wanted to do. We get what is called a latent representation from that, and that can be a really powerful representation of our input data. These are the generative adversarial networks I talked about. The interesting thing to say on this slide is none of these people are real. When I had this slide in 2014, that was a big shock to people. Now people are really familiar with generative AI art, and the fact that none of these people actually exist and they are all generated by artificial intelligence isn't as big of a surprise anymore. So it's getting more and more integrated into what we're trying to do. Okay. The last kind of machine learning that I'll talk about here is reinforcement learning. It's another one of these big, broad categories, right, and it's very different from the other one. So instead of getting some output that you're trying to do, you actually have an agent that interacts with an environment. And when the data that you have there, or the experience, is what happens when the agent interacts with the environment, or the state are talking about here. So the agent does some action, it gets some reward based on the change in state and the environment. And this is where we've seen a lot of advances in robotics. And you may have seen some of those videos of like the little robot like lying on the ground and waving its legs in the air because it's not very good at doing it. But you might have also seen recently some of the videos of robots doing like backflips or carrying boxes around, or doing something interesting like that. And those are all mostly trained with reinforcement learning, where The reward might be based on whether it can stay standing or whether it moves the box. But reinforcement learning creates this really powerful tool where you can actually create something that learns to interact with an environment. And that becomes a really useful tool, especially when you pair it with something like a physics simulation that might exist in a domain. So if you already have something that can kind of get at what a chemical reaction or how an agent is going to interact in an environment, like in agriculture, and you already have physics simulations that can do that, you can look at mitigation tactics. You can give the agent power over mitigating those issues and kind of measure in the simulation how the agent is responding, if it can actually successfully mitigate whatever disaster is pending in there. So it's a very powerful tool. Okay. So getting into the what is actually deep learning. This is a term that gets thrown around a lot. It is just a very specific kind of machine learning model. It's just a bag of statistics. So it's a subset of machine learning algorithms. Looking at the traditional, this is kind of getting into that, do we have to do feature engineering or can we just throw data at it question that was asked earlier? So let's say we have a chemical database. We need to create these molecular descriptors from that chemical database. Historically, how that's been done is through human intelligence. We can then take those molecular descriptors into a machine learning model and get what we want out of that model. What deep learning allows us to do is instead take a raw format of the input data, creating this image, and feeding that into a deep learning network. Going back, we now have taken out this need, this very expensive task of adding human intelligence to this data. So our deep learning model can still do very well, get those features out or get the key features from this grid image and give us an output. Deep learning has had state-of-the-art performance in a lot of historical tasks, and it also has given us the ability to do things that weren't possible, like these generative adversarial networks, like DALL-E, which creates these images from a text input, which is very, very fun and practical in a lot of different ways. Yep. So it's a very powerful tool. Okay. One of the things that comes out with deep learning is it is an incredibly powerful tool, but it also requires a lot of computational processing time. What's interesting is the algorithm that actually is the fundamentals of all of deep learning, or the mathematical principle, was come up with in like the 1950s, and everyone said, wow, that's really cool. Too bad we have to do that like 10,000 times per second for it to be useful for anybody. Well, now we have these huge supercomputers that can do incredibly fast processing. We have access to things like Amazon Web Services, which can give you a infinite amount of compute, assuming your pockets are deep enough. And we have access to all of this data. So one of the really interesting proofs that came out back in the day with deep learning is a neural network is considered a universal approximator, given two very specific things. If you have a sufficiently large network and a sufficiently large amount of data. So if you have infinite data and infinite network, it can predict anything. It can model anything. Of course, we don't deal in infinities in the practical worlds, but the mathematicians love that one. And it is a very interesting paper if you want to look at the universal approximator theory for neural networks. It's very cool. It's also super mathy and nerdy. So if you don't think those things are cool, just trust me, and definitely cool. Yeah. And then there's also all of these models that exist out there. The code is available for them, which is really nice.